Okay. Are the AC is on? Because yesterday it was very hot. Uh, Maybe you have to just press several times. Is this on? This is on, right? Okay, then it should be fine. Somehow yesterday was very hot. Okay, so let's continue with the formulation of quantum mechanics. But before that, is everybody in sync with whatever we discussed till last class? Is there anybody who have still doubts and didn't follow? And this is a good time to resolve all that. Any, even an iota of doubt, feel free to tell me now. Hmm. Yeah, so this is the thing. So I will talk about in detail this issue today. That like, what do we mean by physical distribution, physical explanation? We usually mean something we can directly measure in a device, or we have a analogy in some one level deeper down. So it turns out it doesn't. So what this thing is, it's a prescription. It's a but it is not very surprising. So when you say complex number, you might think, oh, complex numbers are so weird. Why do you have that? But it is not so surprising in the sense, for example, you always need to invent new kind of numbers when you have to describe something more complicated, right? For example, when you are counting objects, right? That's how human being invented numbers, right? When you're counting objects, like how many marbles you have or how many cows you have, so then you need only natural numbers, right? But you want to introduce the operation of subtraction, then natural number is not enough. You need a concept of zero and concept of negative numbers. Now if you want to measure or quantify something that is continuous, like amount of water, amount of milk or something, then you need a real number. Or even you want to do something fractional, that a distance between two places, you need a real number. So that's how you keep expanding the number space, the space of representation of objects, right? So complex number is nothing but a extension of this idea. It's, you need two numbers to describe something. One number is not enough. So you term it as a complex number and define a certain set of rules. And a complex number is nothing but a two-dimensional vector. In that, if you look at the addition rule and all the rules it follows, it's nothing but a two-dimensional vector. So it's not that strange when you try to think of, oh, why do I suddenly need complex number? There are objects like that. You need vectors or kind of structures for that. But why this complex? What is this complex number physically? Okay, so that point is, there is no better explanation than just saying it's a prescription to tell what will you get when you measure, and prescription to tell what is the probability of measuring something. Okay, so that is the best possible physical explanation. What I will try to do today in the later half of this class, I will try to give some physical interpretations. They are not explanations, they are interpretations, because they belong to a regime where you cannot do an experiment. So that is what I'll try to do eventually. And but if you only take things where you can know for sure what is what, and you can do an experiment, then the best thing to say that these are prescription to tell you what will be the probability if you measure something. And that's what we call probability amplitude. We call that wave function, whatever you name them, that's choice. Okay, make sense, or you are not happy? Yes. No difference. That's a choice. So again, as I said, an individually probability amplitudes doesn't matter whether you give a I or not. But when you are adding two states, right? When you are adding two states, then there is a big difference. Like if you are describing something as 1 by root 2 plus z plus I by root 2 minus z, then this combination is a very different combination from this. because they are two completely different objects, right? So and even though when you calculate probability, they will give you the same thing, but when you combine them, like when you sum probability amplitudes and try to calculate a probability of some event that can happen in two ways, so then these things will start mattering, right? So that is another very important point, that the description of a state always have some choice, because that is what we established in last lecture, that there are a lot of choices to how do you describe a particular state, because you always end up with a set of constraint which is much less than number of variables. But once you choose one, once you lock down on a set of choice, then you are bound to make other choices such that the relation between this state with other state is intact, is as per the experiments. Okay? So this is one more important point to note, that these are prescriptions to tell what will happen when you measure something. And that again means that if you are not measuring something in between, you are measuring at the end, or something you don't know which path it takes, then there are rules that when you add probability amplitudes or probabilities, etc., all these things are there. But there are prescriptions for that, and what we establish that you need this kind of structure, complex number, vectors, and all that for that is the whole point of this story. Okay. Yeah. Uh, Still more doubts? It's good if you have questions. And yeah, what is? Huh. Yeah, so superposition of state, it means that, so for example, this line, this equation, it represents a phenomena called superposition of states, because it tells you if the state can be like, if this can be in one of these two possible states, then it is both at the same time until measured. So this is the meaning of superposition. For example, if you think of a superposition in the sense that you are adding these two vectors, that's the mathematical meaning of superposition. No. This is a very wrong way of saying it. Quantum mechanics is not failing in explaining determinism. Quantum mechanics is telling that there is no determinism. So that is the point, that you necessarily need to bring in probability to describe something when you don't know about the state of something. So this is very different from classical. I'm going to talk about it very elaborately today. So if you don't know that, let's say you toss a coin, you don't know whether it is head or tail, but that is your degree of ignorance. That is not what it is actually. Like in principle, if you know all the initial conditions perfectly, you can calculate the dynamics and you can predict whether it will be head or tail, right? So there is a space of initial condition, almost infinite space, like how you put it, whether you angle it like that, what's the air resistance, etc. So many factors. And all these factors lead to two outputs, head or tail. But because of the complexity of this space, you don't know whether it is head or tail, so use probability to describe it. So that is the nature of classical probability. But quantum mechanics suggests that if I tell you with head and tail, you will find it more weird, but instead let me just call it up and down. Okay, but you can call it also, let's say, quantum coin. This is up and down is a quantum coin of head and tail. So here it is telling you that it is not a matter of complexity. It is what a superposition, which means it is both until it is measured. That is what the experiment suggests, and that is what this description implies. So this description is taking into account to that, and I hope I have convinced you through the double slit and Stern-Gerlach that the experiment is consistent with the interpretation of superposition. Okay? So this is a very important difference between classical probability and quantum probability. It is not even like that. It is pending. You can try to think that maybe this thing is doing something like this. So head and tail. Okay, and somehow this is up and down, and it is spending equal amount of time in head and tail state. So that's why when you measure, you are finding it either head or tail. It's not even that. And that is what the experiment also suggests, that yes. until you measure it both up and down. That is the statement, and I hope you are convinced that the experiment implies that. That is very important. It's not a statement that I'm trying to impose on you. Okay? So let's go to the mathematical formalism a little more deeper, and then we'll talk the rest of the class on the interpretation. Okay, I hope everybody, this is very strange, very, very strange. And that's why you need to take it slow and slowly absorb this stuff. Okay, so let's give a generic description of what we developed over last few classes. So generalizing description of a quantum state. So let's put everything in a more abstract and general framework, and then we'll come back to again what does it mean, this question. So the first statement is a quantum state is described by a vector. Again, when I use the word vector, so put it under quote, because we have established it's a, so strictly mathematically these are projective vectors. The projective vectors are rays. Which with abstract notation I can represent it by a psi bra. Now every psi has a dual psi, which is a kate. So this is bra. No, I think this is kate. This is kate. This is bra. This is just splitting these two words, and this is in the same mathematical sense that why do I need a bra and kate? That we have already talked about it, but we need to get a scalar, a number. And why we need a number? Because end of the day, whatever you describe, your measurement is a number. It's a reading. It's a single number, a single quantity, right? So we have to have a mechanism of getting a number out of a vector. So one such mechanism is a dot product, and for that you need a vector and another vector which is in the dual space. Okay? Right? One has to be a row, another has to be column, and so on. Right? Everybody is in the same page. So in the same state, you can describe it in two different ways, and at least two different ways. And then there are of course other ways because it's a projective vector after all, which has a lot of choice on how you choose the phases, etc. So see, this is the first statement: a bra vector or a kate vector is a quantum mechanical state. So this is already different from a classical state. And so for example, a classical state can be also described by a vector, right? In 3D, you need 6 numbers to specify the state, position, and momentum. But that means totally different thing. So if you are describing position, it means the position is like something in this axis, something in this axis, something in this axis. Px I cap, y j cap. So it's position, right? Not momentum. So this is how you describe a position, and similarly you can describe momentum and all that. So this is different from that because, as we already argued, that this is the like completely orthogonal state. Like in this case, for example, like a let me put it. How do I put it in a better language? So something has a coordinate 2 and coordinate 3 in x and y and z direction. So here you can say, okay, this is like when you write it as a superposition, some c1 plus z plus c2 minus z. So this is in that sense, it's similar to two orthogonal direction, but their description is different because here what we are saying, they are in two different states at the same time. Okay, and I will come elaborate more that how it is different from that. Okay, at this point, mathematically they looks identical. So now the next point where they starts becoming different. So the probability amplitude of a particle psi in state of a particle in state psi of a particle in state psi to be found in a state phi is given by phi psi. So this is the necessity that why I need to introduce these dual vectors. So if I ask you that what is the probability amplitude that something in state psi will be found in state phi, you have to calculate this quantity, and we have established this through this example that if this is the case and I ask you what is the probability if I measured plus z, I will find this particle in state psi to be in plus z, and that probability is amplitude is plus z psi c1, and probability is of course square of that. Now you can ask the opposite question that if I replace psi by phi, so the opposite is so phi in psi, then this will be simply this. Just uplift this, and these two are related by this. So one is complex conjugate of the other. Right now, it is not obviously clear that why I am putting up such a rule, but this rule will be clear when you use this in the opposite way. Okay, just take it as a rule for now. And the probability is, so if this is, so this is the probability amplitude, and the probability is just mod square. Okay. So this is what these states are useful for. So again, one more thing I want to be very careful about the word state. So usually, so that is why I think it sounds same as this. So when I say state of a particle, the state of a particle means it has this coordinate. Let's say it is 2i cap plus 3j cap plus 4k cap. So that means it is at position 2 in x-axis, at like scale length 2 at x-axis, scale length 3 in y-axis, and scale length 4 in z-axis. That is what it is, whether you measure or not. Okay. Now that is where this thing is different. The state is this and this. This amplitude is this and this, both at the same time, and it is not a definite state of being because it's a probability. Right? So probability means if you measure, then the probability is to get it in that state. So that is where it is different from that. And in that sense, the word state is a misrepresentation. But due to lack of a better vocabulary, we are using the word state. So this is a problem you will encounter throughout quantum mechanics because we continuously borrowed word from our regular day-to-day language, and we continuously use like classical analogies to describe things, which is totally not correct. But that's how it is. Like when quantum mechanics was developed, maybe 0.1% people in the whole world spoke. I wanted to talk about quantum mechanics, and I think they didn't care to improve the English language or any language to include those words. So usually a language expands by your experience, right? And then there are all kind of peculiar things will appear, and this you have to always keep in mind. In quantum mechanics, a state is not a state of being. A state is a prescription to measure, prescription to tell what is the probability of measuring something in a particular state. This time I'm using the state in classical sense. Okay, so it's a problem. It's a continuous struggle. It's like if you tell someone, because there is nothing like that. So that is the problem. There is nothing like that. If you tell someone, oh, how does this food taste? So they say it is sweet. Then you ask, what is sweet? And then let's say that person has no idea what is sweet. So then you say, oh, that's how sugar tastes like. You say, I never had sugar. Then how will you explain? I mean, it's not that bad, because sweet might have a biochemical definition where you say, okay, this particular molecule, whatever it tastes like. But this is more frustrating than that, because there is nothing analogous. There is nothing to compare it with. This is a completely different paradigm. You are using a word, a classical word state, to describe it, and because you don't have a better word, or you could have came up with another name. You could have called it completely some random. You put your name also in that. Doesn't matter. But this is what it means. When the word state is used in quantum mechanics, this is what it means. It is nothing like a classical state. Okay. I hope everybody is. Huh? Yeah, good question. So this is a vector in the sense it follows the rule of vector algebra. Okay, but it has some additional constant, because it has the requirement that it must represent probability. Right, when squared it represents probability. So it's a normalized vector. It must have length 1, because when you square it, you must get 1, and total square. And second thing is that it's a complex Hilbert space. It's a complex vector space, which is called Hilbert space. So that we established over various experiments over last. So these are the two requirements, but and they are projective, because again, projective in the sense when you describe the full algebra and do all these problems, then how you describe a particular vector is not important, but it is important with respect to other vectors. Once you describe it, you have to set up everything according to that. So they are vectors, they are projective vectors. Whatever you know mathematically as projective vector, they are exactly that. They are nothing different from what you know as projective vectors. Okay. Okay. So when I was I read a book, no, a story. It's written by Satyajit Ray, and I think the book is called. It's a Bengali name. You may not follow the name properly. So it's about an alien and a child, okay? And many people say that the story of E.T. was stolen from that. So there was a section where the alien comes and tell the child. The child asks, "What is your name?" He said, uh, you cannot pronounce my name. We say, how is it possible? Well, then he opens his mouth and show that he has two tongues. So because he has two tongues, he can pronounce something that this guy cannot. Okay? So this is kind of like, you will understand this gradually. One can take this view that the world we experience is a projection of what we can. Okay? And we will see eventually that probably this peculiarity is coming from that. We have certain senses, we have certain ability to describe the world, but that doesn't mean that that is what the world is. That world is probably something else, but what we experience or feel is a projection of what we can. So we'll see that. We'll see this view, that how it appears, why quantum mechanics is so peculiar. Okay, so let's try to set up these rules. And Feynman gave a very, so when you are uncomfortable, think about that why this is a possibility. That's what I'm trying to just heal your frustration. Okay? And so Feynman came up with a very nice analogy. He said that trying to understand nature is like, let's say a child is watching two grandmasters playing chess. And he has no idea that what the rules of chess are. And not only he doesn't, so first of all, they have to figure out from what are the rules of chess by watching the moves. And then the question comes, why it is so? So that is even more order of magnitude difficult question. So this attempt is kind of that kind of attempt. Okay. Okay. So then the third point, the states are, this is actually echoing the first point, arbitrary up to a phase factor. So it is both in global sense and also in local sense. Why it is global sense? Like I can take this and multiply everything. So this psi, so take this psi and multiply it by some e to the power alpha overall. And that doesn't matter. Nothing changes if I do that. Now I can also do, so this is a global factor that is always true, even if you are not looking at the C1 and C2. Now I can also multiply an arbitrary factor here, but that is going to affect all other states. But this global factor is not even going to affect the other states, because when you take inner product, they will cancel out. So this is the degree of arbitrariness, because there is a whole space of, so again, a state, a quote unquote state, can be described by infinitely many vectors, but you have to choose one. Okay. Now 4 is uh, 4 is kind of a big deal, so let me write it on top. Unfortunately, this is a one. This is not a one board class. It requires multiple boards. Unfortunately, I have but don't worry, I will anyway give you the notes. So I hope all of you are logging into Piazza, because I have given all the. You don't have to really copy what I'm writing, because I give the notes and I also specify all the references that I use for a particular lecture. But that doesn't mean you have to use it, but you know that what is there to read. Also, it is almost always true that I deviate from any references, that I don't exactly follow any particular reference either, but what I give is what references help me to prepare for this. Okay. Okay, so now let's say fourth rule. So consider an n-state system. So far we have talked about two-state systems, but let's assume I generalize it. So let's say I have a standard luck device for spin n. Okay, so then there are n outputs. So it is like that. So I will give you an assignment problem for spin 1, which has 3 components. What we did is spin half, and we can do an arbitrary spin like that. So consider an n-state system where an observable. So what is the observable? An observable is something that you can measure. So in this case, the spin is an observable. How you can measure it? By from the deflection of the beam from what it would have been if there was no magnetic field. So that is the definition of an observable. Observable is whatever you can observe or measure. So where an observable A, let's consider it A is spin in this context, and it can take values A1, A2, dot, 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 AN. Okay. Now, this is equivalent to saying the spin can be either plus h bar by 2 or minus h bar by 2. Instead, I am saying it can take n values, just to generalize the picture. And then they are in states A1, A2, and dot. So when that happens, then the C, you can write that psi is a superposition of C1 A1 plus C2 A2 and dot 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 Cn AA. Everybody follow this generalization? It is just a generalization of two-state system. In this, our problem, A is Sz or Sx or Sy, whatever you like. The A1 and A2 are plus h bar by 2 and minus h bar by 2. And A1 and A2 are basically plus z and minus z. Right? This language, I'm just generalizing it for n speed. Okay, so this you can, so this is the fourth rule, which I'm just making them the rules general. So there is a shorthand to write that. Now similarly, you can define a dual vector, which is by this rule, Pi star Ai. Okay. And then you can always take a, so what is this Ci by here? So this Ci is nothing but Ai psi. The probability amplitude of getting Ai when you measure the like probability amplitude of finding the state in the state Ai. So that is the Ci. Okay. Everybody is in sync with the language, what I'm writing and the equation and the way I'm describing it. Okay. So let me write it explicitly. Amplitude of getting, because when you get Ai, that means you measure that particular Ai eigenvalue. Not okay, let's not use the word eigenvalue, that value Ai. I'll come to later why it is eigenvalue. Amplitude of getting Ai if you measure A in a state psi. Okay. Everybody is with me? Okay. So then also you must in again from this understanding, when I'm generalizing, this must be also true. This is just equivalent to saying that plus z is 1, plus z minus z, but plus minus z and minus plus z is 0. So that I'm representing by this delta function. Okay. Every single word you should understand at this stage. So don't like drift away or like think about something else when you are watching. I mean, be mentally present here, not just physically present. Okay, I'm just consolidating everything we learned so far in a general language. Okay, so this thing you can also get very simply by computing by in this line. If you put a AI here, because of this rule, if you put a AI here, because of this rule, you will get only one particular. So let's not use AI. Let's give AK. So if I do AK psi, then you get CI AK AI, right? But AK AI is delta AK, it's KI. So CI delta KI, I. So that is CK. Okay? So you just get from this calculation what is the probability amplitude of finding the state psi in AK. So it's consistent with how we define space. Now you can also calculate an expectation value, because the expectation value is what we discussed also. This thing is because now it takes value AI with probability Ci square, just the classical meaning of expectation. And it must satisfy this, that psi is 1 because they are normalized. They represent probability. How will that happen? In order that to happen, you have to have AI Ci star Ci AI. Actually, to be very precise, you should put a AK and CK and sum over all K and I. Now this thing, because of this guy, they are numbers, they will come out. But this will be a delta function and you will be finishing with Ci mod square sum of I, and that must be 1. That is also to say that your C1 square and C2 square in this case must be such that their sum of square is 1. Okay. So this is just half a page of rules. I hope you just understood it. It takes half a page to write. It's that easy. Okay. Now let's talk about one more thing, which is an axiom, and it's more mathematical, but it's naturally fits into this description. And then the rest of the class, I will talk about the best possible way I can on physical interpretations. So this is, I think, the physical interpretation part. I can assure you, it will take a while. You will may not be convinced, even if I tell you. Okay. So in next class onwards, I will actually talk about a very mathematically um, accurate description of this. Right now, what I'm doing, I am doing this, taking this chess player approach, which is trying to develop a description from what I observed. Next class, I'll give you a very tight definition in terms of method using proper rules of linear algebra. But this is something you should know that, and this is often like you also a mathematician, right? So the mathematics students will find frustrating this part because in at least in context of quantum mechanics, but in many other context of physics, the physicist doesn't go from point A to B always in mathematically same way. I mean, they go by some intuition and logic, which is doesn't make sense. So there is a whole formalism method of quantum mechanics called path integral, where Feynman introduced some notion which is totally mathematically ill-defined, and it doesn't make any sense mathematically, but it gives you accurate result that matches with experiments. So it's a open problem, and many work happened after that to find it mathematically. I don't know what is the current status, but there are some partial progress, and it's a field of mathematics where you called functional algebra. So it's a now kind of well defined, I think. But this is the approach of a physicist, and there is a story that you know about Harish Chandra. The Harish Chandra Research Institute is made up. So he went to do a PhD with, I think, Pauli, and he was very frustrated with this approach. And why the physicists do that? So he said, I don't like this. He said, okay, then you go to mathematics. So he went to mathematics and became a very good, famous mathematician. And the opposite thing happened to Feynman, because he went to do mathematics, but he didn't like the too much rigor. So then he was advised to go to physics. So he went to physics. So physicists have always a different style of doing mathematics, which is kind of partially intuitive and not always derivation and definition and not so rigorous. I think it's kind of important to make progress. Otherwise, if you spend a lot of time thinking what is differentiable, you may not ever differentiate anything. So it is kind of the approach is like that. So then I want to talk about another thing called completeness. We all have a finite lifetime, so we have to think about how we can go without making a mistake, of course. This is also very interesting to understand. The synergy between mathematics and physics is always very interesting. That when Heisenberg wrote down the matrix mechanics, he had to write down the numbers of certain structures in a way which looks like a matrix, and he didn't know what is matrix. But he turned out to be matrix later. So linear algebra was properly developed not very long ago. So those people were using it, but initially without knowing. Then they started using it that the structure is already there. This beautiful structure of linear algebra was already there, and then they started using it in quantum mechanics. But initially they didn't use it. The quantum mechanics was formulated in a very different way. And this is true in many other contexts, like where like calculus was developed, of course, after feeling the need of it to describe dynamics and all. I mean, if you are a Newton believer, but if you are what is the other guy who is credited for calculus? Huh? Leibniz, right? So I think if he developed it completely independently, not in connection with dynamics. But Newton developed it in connection with dynamics. So this kind of thing happens all the time. There are many other similar examples. Okay, so completeness is the fact that if state of basis, the space of basis states forms a complete vector space. Okay? forms a complete set of states. Now this is a jump, and this is an assumption which fits nicely with the description of quantum mechanics, and it is not so easy to think of when you do certain continuous system. Like for discrete system, it's kind of easy to see, but continuous system, it is not easy. So we kind of take a leap of faith and make it work, and it turns out that it works somehow. Also, in next class, I will tell you also about another issue, that when you try to describe the set of continuous states, then all this set of rules I wrote down, at least one of these rules starts fuzzing around. So then you extend that definition. So this is again how physicists do mathematics. Like you tweak the definition to fit the physical nature, okay? Because the nature doesn't necessarily follow how you set up things. There is an interesting story in an article written by Wigner about this. So I think the story is following that how mathematics shows up in a weird way that doesn't, it's not easy to say whether mathematics is an invention or it's a discovery, right? In the sense that whether mathematics is already there in the nature somehow, and you are finding it, or whether you invented it as a language to describe nature. So the story goes as following. So there were two friends who were, I think some of you attended the Sunil Mukhi's talk. He described a lot about all these things a few days ago, the physics club. So the story is like that. These two friends, one of them was very good in math, another was very good in arts. And they were very bad in the other subject, which is whatever, like math guy is very bad in art and art guy is very bad in math. So they parted ways after a certain point, and the art guy never studied math after school, and math guy also never studied art, and they met a long time back. So now the background of the story is important to tell, that the art guy doesn't know anything about math. So the math guy became a statistician, and the art guy became an artist. So the art guy was showing his artwork. So the math guy also felt that I need to show something. So he showed his paper, and that paper was on income distribution of people in a certain city, and that has a Gaussian structure. And the formula of Gaussian is 1 by root 2 pi e to the power minus x minus mu square by 2 sigma square, right? So he asked the art guy, what is mu, what is sigma? So they said, okay, this is mu, this is sigma. Then said, what is pi? And the pi is the ratio of a circle's periphery and diameter. I said, what is a circle doing in income distribution? So that question is not easy to answer. Where did the circle show up? That when you are counting number of people getting a certain amount of money. Now, of course, we know how the circles show up, because the way you are deriving it, this formula, is by taking this, by rotating this curve, and then finding this, then taking a square root of it. Now, how the income distribution knows that you are going to derive it in this way? So this is a very strange question, and there is no good answer to that. Okay, so somehow there is a weird connection between things which you don't know, which is not easy to explain. Okay? Anyways, let's say detour to make sure you are not sleeping. Okay, so the completeness tells you, so any state, so this is a axiom which comes from partly from mathematics, but it fits with this description of states as we wrote. Any state can be written as a superposition of basis vectors, which means the psi, this simple statement, that CIAI, that any state can be written. So this is equivalent to saying, if you know all the basis vector in a space, then any vector can be written as a superposition of basis vectors, right? All of you know this statement. So this is just to say this statement. So now how do you know that plus z and minus z are forming basis vector? You know it from the experiment, but it's possible that you discover another state. But as we know, this particular experiment, only there are two states, two possible states, plus z and minus z. So any state of those particles which are spin half, they can be expressed in a superposition of those basis vector. If there's some higher spin, then you need more basis vector. So this is the statement. Okay. Now they must follow, the basis vector must follow this orthogonality. And then there is a idea called resolution of identity. It is just to say, I will come to in elaborate description of what does it mean, but let me state you that quickly as an example. So if I write class Z, so this must be equal to 1. So you should be able to, this is a mathematical result, and this you can write it. So let's say I choose to write the plus Z, I represent it as 1 0, yeah? And minus Z as 0 1. 2 by 1 vectors. It's a representation. So far I never used any representation. I did everything abstractly. Now I'm doing a representation. So the psi must be a superposition of C plus Z plus C minus Z. So I should be able to write it as C plus 1 0, C minus 0 1. So then this resolution of identity is telling me these vectors which forms a basis vector, they must satisfy this identity if they form a complete set of vectors. This is a completeness axiom, and that means I can do this calculation plus Z plus minus Z to be 1. So are you familiar with this kind of products, outer products? So plus Z is so inner product is like this 1 0 1 0, right? So this is ulta. This is 1 0 1 0 plus 0 1 0 1. So this works like this. So 1 has to be multiplied as this. So this 1 into 1 is 1. 1 into 0 is 0. 0 into 1 is 0, and 0 into this is 0. Similarly, this will give 0 into 0 0. 0 into 1 0. 1 into 0 0, and 1 into 1. So these two added is 1 1 0 0. Identity. So this is the meaning of this statement. It is just a example of that general statement. Okay. Everybody knows this kind of product, inner product and outer product. Okay, don't hesitate to tell me you don't know, because it's very important. I'm going to use it many times. Okay, so if this is true, then I can put an identity anywhere, right? So I can put this psi, I can write it psi is 1 times psi, no problem, because it's a general identity. Identity is ai times ai psi. So this statement appears naturally then. So this is ci. So then it is ci ai. So this is just a restatement of what I said already, but in a more mathematically precise language. Okay, using this identity. Okay, now let's talk about. I'm more or less, I said everything I wanted to say in the mathematical part. Now let's talk about interpretations. Unfortunately, I have only about 10 minutes. This actually requires a lot more discussion, and I will give you a pre-recorded lecture where I discuss it almost for an hour. So let's go over this again. So we already talked about that, how this thing is different. So if I have a representation like this, and if it is so, if more than one ci is not equal to 0, which means this is not a state exactly in one of those basis state. More than, so ai can take any value, ci's can take any value as long as sum of ci square is 1, and it can be 1 at 1 for one I and 0 for everything else. Then it's not a problem, it's a definite state. But if it is not, then it's a superposition state, right? So note that this is nothing like classical superposition. Why not? Because in classical superposition, when I say the probability of getting head and tail, if you sum them, it's 1. Right? There is nothing beneath that. So here it is one thing happening beneath that, which is the CI, and they are responsible for how you handle things when there are multiple ways things can happen without measurement. Okay, so this is one point I want to um, you to note down, and notice that this is more strange because you need these. So for example, we discussed this, that plus x could be 1 by root 2 plus z and 1 by root 2 minus z, and plus y could be that I by root 2. So you need a completely different kind of thing. You need a complex number to describe this. This is something we have already described. And there is no analogy for that in the classical probability or classical superpositions, you know. Okay? And this is something I already emphasized, that this is a prescription to describe that what you will see in an experiment. Okay. Now, at this point, one must be very careful about having a picture. Like you might want to have a picture of what is happening. So one classic picture is through Schrodinger cat experiment, which let me describe it a little bit. So again, what I'm going to tell is different way to say the same thing to describe the same situation, such that just you understand this a little better. But this is not anything new, what is already stated. There is nothing more to say because there is nothing known beyond that. What is known beyond that are speculations. So I'm going to tell you a little bit about speculation. And I'm going to give you two interpretations. One is called Copenhagen interpretation, another is called many world interpretation. The many world is very fascinating, but it's still a way of saying what is being already said, nothing more than that. So let me talk about the Copenhagen first. So I will like to talk about it in terms of this Schrodinger's cat experiment, which you might know, some of you already. So the experiment is following. So let's say there is a box, and the box has a cat, okay, and there is a radioactive element there. So let me call it some radioactive element which releases radioactive particle. They are detected in some Geiger counter, and this is a probabilistic event in a short time. Of course, if you have a radioactive element, and it's still probabilistic, because if you wait for very long time, then you know almost surely something will be detected. But in a short time, it's a probabilistic matter whether a radioactive particle is detected here or not. And if it detects, then there is a circuit that, so let's say some poison is kept here and in a glass box, and a circuit triggers that when it gets something is radioactive detected here, breaks the box, and the poisonous gas releases and the cat is killed. Okay? So this is what the setup that Schrodinger described. Now, if you ask that is the cat dead or alive if you have not opened the box, so then the classical interpretation will tell you the cat is either dead or alive, right? Until you have opened, even if you have not opened the box, just that you don't know it. So you describe it that there is some probability. So this is the state dead and this is the state alive. So two states. And you say there is a probability that it is dead, there is a probability it is alive, but it is because you didn't open the box. But whether it is dead or alive, that already happened in the box. Okay, so this is the classical interpretation. But the quantum statement is following: it is both dead and alive until you have opened, both at the same time. This is very strange and very peculiar. So if I want to write it in sync with how I wrote things earlier, so the state of the cat is something like this. 1 by root 2 I am writing because I am assuming equal probability, but it could be anything else. Okay. So what this interpretation is from Copenhagen School of Physics, and Bohr was the person who described this. And what he said, that was it Bohr? Yeah, I think it was Bohr. No, it was Schrodinger. No, it was Schrodinger's cat experiment. So what he said, that the language he used to describe this phenomena is said, when you open the box, then you find it is either dead or alive. There is no way you can find anything else. That is the classical observation. So this thing is the cat is both dead and alive until you open. And when you open, it collapses into one of these states. Collapses into one of these states. So when you open in a given experiment, you observed it either dead or alive. But to describe the fact whether it is dead or alive, you need this idea that it is both dead and alive until you open. Now it sounds very strange when I talk in terms of cat, but that is what these Schrodinger experiments are, all these Sternberg experiments are suggesting. If I call the up state a dead state and down state a alive state, that's what it is suggesting, that it is both dead and alive until you have observed that whether it is up or down. So this language they use is the language it's called collapsing into one of these states. The state collapses there. Now this is nothing but a description. It is not a explanation. Okay. So the statement is act of observation collapses. So, act of observation collapses. Okay. Cause collapse. Now it is not very satisfactory yet. So then there was a very attractive description, but that description has some problem. Although it is very attractive, came from Everett. I think it was a PhD thesis from Princeton in 50s. So Everett came up with the explanation that how is it possible the same thing at same place at same time is dead and alive both, right? How that can happen in your classical way of thinking. So what Everett said, he came up with something called many world. Everett. Again, this is an unfalsifiable scenario that is probably true or not, but there is no way to say that. But it's a little more satisfactory than this, but it runs into various other problems. So what he said that that there is no concept of collapse according to him, because it's the observer is now part of the system in Everett's picture. So what he said, so let's say the situation is like that there is a timeline of events. Okay, so this is a box with cat, with poison, etc., and the observer who is watching it. Okay, an observer who is watching it is itself now part of the description. Now there is a point when the observation happened. Now at this point the universe splits into two universes. In one part the cat is dead. Okay, observer observing the cat is dead. In another universe the observer is observing that the cat is alive. Okay, so this is a theory of multiverse. There are multiple universes at the same time at the same place which are not connected, which means there is no communication between two universes. There is no communication. Now if that is true, then it makes sense to say that something can be both dead and alive at the same time. Now when you open the box, you are a part of this universe, which let's say you have observed it to be alive. So your storyline continues from there. And this, you have no access to this storyline, which is happening somewhere else. Okay? It's very attractive idea and heavily exploited in Hollywood, but there is no way to say if it is true or not, because he protected the thing by saying there is no way to know. There is no communication between universes. But of course, what Hollywood does is, what is this character Strangelove, right? He can travel between universes. This Marvel and DC, they heavily exploited this idea. So there is a paper which I'll send you in the Piazza or something, and there are multiple papers. So you try to use this idea to precisely nail down double slit, you run into various problems. But it's an attractive idea that kind of tells you how it might be possible to have this. Now there are many other interpretations. There is another interpretation called Wigner's friend, which says that, so let's say this person who is watching this is Wigner. Okay? Wigner came up with this idea. And Wigner's friend is watching Wigner. Okay? So the fact that Wigner observed dead and alive, there are two states for Wigner's friend. So Wigner's friend, it's still a superposition until he knows whether Wigner observed dead or alive. Okay? Then you can think there is a Wigner's friend's friend who is watching Wigner's friend, right? So that way you can keep going. There are infinite friends, and there is a super observer who observes everything. And if you want to interpret with some religion, then you can say the super observer might be your God. So, then you get a different meaning of the word that says God is observing everything. Yeah? So anyway, again, this part is religion-like because there is not you cannot falsify any of this claim. So it's matter of what you believe in. And okay, I wanted to tell a little bit more. And there are many other interpretations. There is an interpretation using decoherence. There is an interpretation using pilot wave theory. There is a hidden variable theory, which is one way of saying that maybe there is something hidden which is controlling everything, that you are not seeing a complete theory. Basically, you are seeing a projection or a partial theory. It's quite possible. That is why things are looking strange. And at the beneath everything, everything is like what you expect in classical world. Now, this is again, so another school of thought might say that there is nothing classical, like there is nothing like that. It's possible that everything looks strange because the universe is a projection of what it is, a projection of what we can think or imagine in our equipments, which is brain and all other senses. And even if I think of detectors, like let's say let's say we have 5 senses, right? And they are extended senses. Like, for example, if you are wearing a spectacle, you cannot see something, but with spectacle you can see something, right? So that's like an extended sense. Similarly, a telescope can, like the Hubble telescope can see something, but when you advance in technology, the James Webb can see more. So if I conclude, but it's still like extended senses. What you can are extended senses. But it's possible that the universe is what we describe, what we are describing about the universe is whatever we can capture in our all these extended senses. And it might not be the complete story. It's possible there is something hidden, and because it's a partial projected theory of something down there, it is appearing to be strange. So that is one school of thought. So that tells you there is no way to tell until you have some way to access that. But another school of thought can say that it is how it is. But as I wanted to emphasize, that there is no way to, you may subscribe one of this theory, but there is no logical reason. That's why it becomes like a religion. Right? So you cannot, why you choose this idea, not that, there is no logical reason for that. Normally the language we use in physics is this collapse language, but that is just to go along, okay? Because it's popular. So this is all I wanted to say about the interpretations, and I will say a very little. Let's see, someone is waiting. Okay, another minute. Okay. So it turns out this is not the only formulation. But that counts as observation, right? That counts as taking one of the storyline where you watch the cat to be dead or alive. Okay? It is again, you are going to that, imagine double slit. When you put a photon source, you are watching something, and then you know which slit, then it is no longer a superposition. Again, if you can do a Stern-Gerlach with the cats, then you can bring analogy with all these dead alive things. So then it means, but dead alive are only 2 states. You need another 2 states to describe this. These are analogy. If you want to precisely nail it down, then you have to bring some more attributes other than dead and alive. Okay, so it turns out there are 9 formulations of quantum mechanics. There are different ways to describe this reality, whatever you know. Okay? This is something very important to understand. So this is, let's say, this is the sphere of what you are saying. This is our axioms of quantum mechanics, and this is where experiments stop. Okay? There is no experiment to go here. So that's where all this interpretation. And we will not go further in this. People are waiting actually. We'll talk about it later. So there is no way to go further than this. So that part is all about interpretation, and we will not talk about it in this class. Maybe some we can discuss it elsewhere. Okay. So I think that's where we should stop for today. And remember Saturday there is a class, okay? Because I am not there in September for some time. I am yet to figure out how that class will happen. If I get a room, it will be like this from there. But or if I don't get a room, I'll teach in tablet. Yeah, just a second.